The Rise and Progress of Paleontology. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. The Rise and Progress of Paleontology by Thomas Henry Huxley. Essay number 2 from Science and Hebrew Tradition. That application of the sciences of biology and geology, which is commonly known as paleontology, took its origin in the mind of the first person who, finding something like a shell, or a bone, naturally embedded in gravel or rock, indulged in speculations upon the nature of this thing which he had dug out, this fossil, and upon the causes which had brought it into such a position. In this rudimentary form, a high antiquity may safely be ascribed to paleontology, inasmuch as we know that, 500 years before the Christian era, the philosophic doctrines of Xenophanes were influenced by his observations upon the fossil remains exposed in the quarries of Syracuse. From this time forth, not only the philosophers, but the poets, the historians, the geographers of antiquity occasionally refer to fossils, and, after the revival of learning, lively controversies arose respecting their real nature. But hardly more than 2 centuries have elapsed since this fundamental problem was first exhaustively treated. It was only in the last century that the archaeological value of fossils, their importance, I mean, as records of the history of the earth, was fully recognized. The first adequate investigation of the fossil remains of any large group of vertebrated animals is to be found in Cuvier's Recherches sur les ossements fossiles, completed in 1822, and so modern is stratigraphical paleontology that its founder, William Smith, lived to receive the just recognition of his services by the award of the first Wollaston Medal in 1831. But although paleontology is a comparatively youthful scientific specialty, the mass of materials with which it has to deal is already prodigious. In the last 50 years the number of known fossil remains of invertebrated animals has been trebled or quadrupled. The work of interpretation of vertebrate fossils, the foundations of which were so solidly laid by Cuvier, was carried on, with wonderful vigor and success, by Agassiz in Switzerland, by von Meyer in Germany, and last but not least by Owen in this country, while in later years a multitude of workers have labored in the same field. In many groups of the animal kingdom the number of fossil forms already known is as great as that of the existing species. In some cases it is much greater, and there are entire orders of animals of the existence of which we should know nothing except for the evidence afforded by fossil remains. With all this it may be safely assumed that, at the present moment, we are not acquainted with a tittle of the fossils which will sooner or later be discovered. If we may judge by the profusion yielded within the last few years by the tertiary formations of North America, there seems to be no limit to the multitude of mammalian remains to be expected from that continent. An analogy leads us to expect similar riches in Eastern Asia, whenever the tertiary formations of that region are as carefully explored. Again, we have as yet almost everything to learn respecting the terrestrial population of the Mesozoic epoch, and it seems as if the western territories of the United States were about to prove as instructive in regard to this point as they have in respect of tertiary life. My friend Professor Marsh informs me that, within 2 years, remains of more than 160 distinct individuals of mammals, belonging to 20 species and 9 genera, have been found in a space not larger than the floor of a good-sized room, while beds of the same age have yielded 300 reptiles, varying in size from a length of 60 feet or 80 feet to the dimensions of a rabbit. The task which I have set myself tonight is to endeavor to lay before you, as briefly as possible, a sketch of the successive steps by which our present knowledge of the facts of paleontology and of those conclusions from them which are indisputable has been attained. And I beg leave to remind you, at the outset, that in attempting to sketch the progress of a branch of knowledge to which innumerable labors have contributed, my business is rather with generalizations than with details. It is my object to mark the epochs of paleontology, not to recount all the events of its history. That which I must now call the fundamental problem of paleontology, the question which has to be settled before any other can be profitably discussed, is this: what is the nature of fossils? Are they, as the healthy common sense of the ancient Greeks appears to have led them to assume without hesitation, the remains of animals and plants? Or are they, as was so generally maintained in the 15th, 16th, and 17th centuries, mere figured stones, portions of mineral matter which have assumed the forms of leaves and shells and bones, just as those portions of mineral matter which we call crystals take on the form of regular geometric solids? Or again, are they, as others thought, the products of the germs of animals and of the seeds of plants, which have lost their way, as it were, in the bowels of the earth, and have achieved only an imperfect and abortive development? It is easy to sneer at our ancestors for being disposed to reject the first in favor of one or other of the last two hypotheses, but it is much more profitable to try to discover why they, who were really not one whit less sensible persons than our excellent selves, should have been led to entertain views which strike us as absurd. The belief in what is erroneously called spontaneous generation, that is to say, in the development of living matter out of mineral matter, apart from the agency of pre-existing living matter, as an ordinary occurrence at the present day, which is still held by some of us, was universally accepted as an obvious truth by them. They could point to the arborescent forms assumed by hoar frost and by sundry metallic minerals as evidence of the existence in nature of a plastic force, competent to enable inorganic matter to assume the form of organized bodies. Then, as everyone who is familiar with fossils knows, they present innumerable gradations, from shells and bones which exactly resemble the recent objects, to masses of mere stone which, however accurately they repeat the outward form of the organic body, have nothing else in common with it, and thence to mere traces and faint impressions in the continuous substance of the rock. What we now know to be the results of the chemical changes which take place in the course of fossilization, by which mineral is substituted for organic substance, might, in the absence of such knowledge, be fairly interpreted as the expression of a process of development in the opposite direction, from the mineral to the organic. Moreover, in an age when it would have seemed the most absurd of paradoxes to suggest that the general level of the sea is constant, while that of the solid land fluctuates up and down through thousands of feet in a secular ground swell, it may well have appeared far less hazardous to conceive that fossils are sports of nature than to accept the necessary alternative, that all the inland regions and highlands, in the rocks of which marine shells had been found, had once been covered by the ocean. It is not so surprising, therefore, as it may seem at first, that although such men as Leonardo da Vinci and Bernard Palissy took just views of the nature of fossils, the opinion of the majority of their contemporaries set strongly the other way, nor even that error maintained itself long after the scientific grounds of the true interpretation of fossils had been stated, in a manner that left nothing to be desired, in the latter half of the 17th century. The person who rendered this good service to palaeontology was Nicolaus Steno, professor of anatomy in Florence, though a Dane by birth. Collectors of fossils at that day were familiar with certain bodies called glossopetrae, and speculation was rife as to their nature. In the first half of the 17th century, Fabio Colonna had tried to convince his colleagues of the famous Accademia dei Lincei that the glossopetrae were merely fossil sharks' teeth, but his arguments made no impression. 50 years later, Steno reopened the question, and by dissecting the head of a shark and pointing out the very exact correspondence of its teeth with the glossopetrae, left no rational doubt as to the origin of the latter. Thus far, the work of Steno went little further than that of Colonna, but it fortunately occurred to him to think out the whole subject of the interpretation of fossils, and the result of his meditations was the publication in 1669 of a little treatise with the very quaint title of De Solido Intra Solidum Naturaliter Contento. The general course of Steno's argument may be stated in a few words. Fossils are solid bodies which, by some natural process, have come to be contained within other solid bodies, namely, the rocks in which they are embedded, and the fundamental problem of palaeontology, stated generally, is this: "Given a body endowed with a certain shape and produced in accordance with natural laws, to find in that body itself the evidence of the place and manner of its production." The only way of solving this problem is by the application of the axiom that "like effects imply like causes," or, as Steno puts it, in reference to this particular case, that, bodies which are altogether similar have been produced in the same way. Hence, since the glossopetrae are altogether similar to sharks' teeth, they must have been produced by shark-like fishes. And since many fossil shells correspond, down to the minutest details of structure, with the shells of existing marine or freshwater animals, they must have been produced by similar animals. And the like reasoning is applied by Steno to the fossil bones of vertebrated animals, whether aquatic or terrestrial. To the obvious objection that many fossils are not altogether similar to their living analogues, differing in substance while agreeing in form, or being mere hollows or impressions, the surfaces of which are figured in the same way as those of animal or vegetable organisms, Steno replies by pointing out the changes which take place in organic remains embedded in the earth, and how their solid substance may be dissolved away entirely, or replaced by mineral matter, until nothing is left of the original but a cast, an impression, or a mere trace of its contours. The principles of investigation thus excellently stated and illustrated by Steno in 1669 are those which have, consciously or unconsciously, guided the researches of palaeontologists ever since. Even that feat of palaeontology which has so powerfully impressed the popular imagination, the reconstruction of an extinct animal from a tooth or a bone, is based upon the simplest imaginable application of the logic of Steno. A moment's consideration will show, in fact, that Steno's conclusion that the glossopetrae are sharks' teeth implies the reconstruction of an animal from its tooth. It is equivalent to the assertion that the animal, of which the glossopetrae are relics, had the form and organization of a shark, that it had a skull, a vertebral column, and limbs similar to those which are characteristic of this group of fishes, that its heart, gills, and intestines presented the peculiarities which those of all sharks exhibit. Nay, even any hard parts which its integument contained were of a totally different character from the scales of ordinary fishes. These conclusions are as certain as any based upon probable reasonings can be. And they are so, simply, because a very large experience justifies us in believing that teeth of this particular form and structure are invariably associated with the peculiar organization of sharks, and are never found in connection with other organisms. Why this should be we are not at present in a position even to imagine. We must take the fact as an empirical law of animal morphology, the reason of which may possibly be one day found in the history of the evolution of the shark tribe, but for which it is hopeless to seek for an explanation in ordinary physiological reasonings. Every one practically acquainted with palaeontology is aware that it is not every tooth nor every bone which enables us to form a judgment of the character of the animal to which it belonged, and that it is possible to possess many teeth and even a large portion of the skeleton of an extinct animal, and yet be unable to reconstruct its skull or its limbs. It is only when the tooth or bone presents peculiarities, which we know by previous experience to be characteristic of a certain group, that we can safely predict that the fossil belonged to an animal of the same group. Any one who finds a cow's grinder may be perfectly sure that it belonged to an animal which had 2 complete toes on each foot and ruminated. Any one who finds a horse's grinder may be as sure that it had 1 complete toe on each foot and did not ruminate. But if ruminants and horses were extinct animals of which nothing but the grinders had ever been discovered, no amount of physiological reasoning could have enabled us to reconstruct either animal, still less to have divined the wide differences between the two. Cuvier, in the Discours sur la révolution de la surface du globe, strangely credits himself, and has ever since been credited by others, with the invention of a new method of palaeontological research. But if you will turn to the Recherches sur les ossements fossiles and watch Cuvier, not speculating but working, you will find that his method is neither more nor less than that of Steno. If he was able to make his famous prophecy from the jaw which lay upon the surface of a block of stone to the pelvis of the same animal which lay hidden in it, it was not because either he or any one else knew or knows why a certain form of jaw is, as a rule, constantly accompanied by the presence of marsupial bones, but simply because experience has shown that these two structures are coordinated. The settlement of the nature of fossils led at once to the next advance in palaeontology, viz. Its application to the deciphering of the history of the earth. When it was admitted that fossils are remains of animals and plants, it followed that, in so far as they resemble terrestrial or freshwater animals and plants, they are evidences of the existence of land, or fresh water, and in so far as they resemble marine organisms, they are evidences of the existence of the sea at the time they were parts of actually living animals and plants. Moreover, in the absence of evidence to the contrary, it must be admitted that the terrestrial or the marine organisms implied the existence of land or sea at the place in which they were found while they were yet living. In fact, such conclusions were immediately drawn by everybody, from the time of Xenophanes downwards, who believed that fossils were really organic remains. Steno discusses their value as evidence of repeated alteration of marine and terrestrial conditions upon the soil of Tuscany in a manner worthy of a modern geologist. The speculations of De Maillet, in the beginning of the 18th century, turn upon fossils, and Buffon follows him very closely in those two remarkable works, the Théorie de la Terre and the Époque de la Nature, with which he commenced and ended his career as a naturalist. The opening sentences of the Époque de la Nature shows us how fully Buffon recognized the analogy of geological with archaeological inquiries. Quote, "As in civil history we consult deeds, seek for coins, or decipher antique inscriptions in order to determine the epochs of human revolutions and fix the date of moral events, so, in natural history, we must search the archives of the world, recover old monuments from the bowels of the earth, collect their fragmentary remains, and gather into one body of evidence all the signs of physical change which may enable us to look back upon the different ages of nature. It is our only means of fixing some points in the immensity of space, and of setting a certain number of waymarks along the eternal path of time." Unquote. Buffon enumerates 5 classes of these monuments of the past history of the earth, and they are all facts of palaeontology. In the first place, he says, shells and other marine productions are found all over the surface and in the interior of the dry land, and all calcareous rocks are made up of their remains. Secondly, a great many of these shells which are found in Europe are not now to be met with in the adjacent seas, and in the slates and other deep-seated deposits there are remains of fishes and of plants of which no species now exist in our latitudes, and which are either extinct or exist only in more northern climates. Thirdly, in Siberia and in other northern regions of Europe and of Asia, bones and teeth of elephants, rhinoceroses, and hippopotamuses occur in such numbers that these animals must once have lived and multiplied in those regions, although at the present day they are confined to southern climates. The deposits in which these remains are found are superficial, while those which contain shells and other marine remains lie much deeper. Fourthly, tusks and bones of elephants and hippopotamuses are found not only in the northern regions of the Old World, but also in those of the New World, although at present neither elephants nor hippopotamuses occur in America. Fifthly, in the middle of the continents, in regions most remote from the sea, we find an infinite number of shells, of which the most part belong to animals of those kinds which still exist in southern seas, but of which many others have no living analogues, so that these species appear to be lost, destroyed by some unknown cause. It is needless to inquire how far these statements are strictly accurate. They are sufficiently so to justify Buffon's conclusions that the dry land was once beneath the sea, that the formation of the fossiliferous rocks must have occupied a vastly greater lapse of time than that traditionally ascribed to the age of the earth, that fossil remains indicate different climatal conditions to have obtained in former times, and especially that the polar regions were once warmer, that many species of animals and plants have become extinct, and that geological change has had something to do with geographical distribution. But these propositions almost constitute the framework of palaeontology. In order to complete it, but one addition was needed, and that was made in the last years of the 18th century by William Smith, whose work comes so near to our own times that many living men may have been personally acquainted with him. This modest land surveyor, whose business took him into many parts of England, profited by the peculiarly favourable conditions offered by the arrangement of our secondary strata to make a careful examination and comparison of their fossil contents at different points of the large area over which they extend. The result of his accurate and widely extended observations was to establish the important truth that each stratum contains certain fossils which are peculiar to it, and that the order in which the strata, characterized by these fossils, are superimposed one upon the other, is always the same. This most important generalization was rapidly verified and extended to all parts of the world accessible to geologists, and now it rests upon such an immense mass of observations as to be one of the best established truths of natural science. To the geologist the discovery was of infinite importance, as it enabled him to identify rocks of the same relative age, however their continuity might be interrupted or their composition altered. But to the biologist it had a still deeper meaning, for it demonstrated that, throughout the prodigious duration of time registered by the fossiliferous rocks, the living population of the earth had undergone continual changes, not merely by the extinction of a certain number of the species which had at first existed, but by the continual generation of new species, and the no less constant extinction of old ones. Thus the broad outlines of palaeontology, in so far as it is the common property of both the geologist and the biologist, were marked out at the close of the last century. In tracing its subsequent progress, I must confine myself to the province of biology, and indeed to the influence of palaeontology upon zoological morphology. And I accept this limitation the more willingly, as the no less important topic of the bearing of geology and of palaeontology upon distribution has been luminously treated in the address of the President of the Geographical Section. The succession of the species of animals and plants in time being established, the first question which the zoologist or the botanist had to ask himself was, what is the relation of these successive species one to another? And is it a curious circumstance that the most important event in the history of palaeontology, which immediately succeeded William Smith's generalization, was a discovery which, could it have been rightly appreciated at the time, would have gone far towards suggesting the answer, which was in fact delayed for more than half a century. I refer to Cuvier's investigation of the mammalian fossils yielded by the quarries in the older tertiary rocks of Montmartre, among the chief results of which was the bringing to light of two genera of extinct hoofed quadrupeds, the Anoplotherium and the Palaeotherium. The rich materials at Cuvier's disposition enabled him to obtain a full knowledge of the osteology and of the dentition of these two forms, and consequently to compare their structure critically with that of existing hoofed animals. The effect of this comparison was to prove that the Anoplotherium, though it presented many points of resemblance with the pigs on the one hand and with the ruminants on the other, differed from both to such an extent that it could find a place in neither group. In fact, it held in some respects an intermediate position, tending to bridge over the interval between these two groups, which in the existing fauna are so distinct. In the same way, the Palaeotherium tended to connect forms so different as the tapir, the rhinoceros, and the horse. Subsequent investigations have brought to light a variety of facts of the same order, the most curious and striking of which are those which prove the existence, in the Mesozoic epoch, of a series of forms intermediate between birds and reptiles, two classes of vertebrate animals which at present appear to be more widely separated than any others. Yet the interval between them is completely filled, in the Mesozoic fauna, by birds which have reptilian characters on the one side, and reptiles which have ornithic characters on the other. So again, while the group of fishes termed ganoids is at the present time so distinct from that of the dipnoi or mudfishes that they have been reckoned as distinct orders, the Devonian strata present us with forms of which it is impossible to say with certainty whether they are dipnoi or whether they are ganoids. Agassiz's long and elaborate researches upon fossil fishes, published between 1833 and 1842, led him to suggest the existence of another kind of relation between ancient and modern forms of life. He observed that the oldest fishes present many characters which recall the embryonic conditions of existing fishes, and that, not only among fishes, but in several groups of the invertebrata, which have a long palaeontological history, the latest forms are more modified, more specialized than the earlier. The fact that the dentition of the older tertiary ungulate and carnivorous mammals is always complete, noticed by Professor Owen, illustrated the same generalization. Another no less suggestive observation was made by Mr. Darwin, whose personal investigations during the voyage of the Beagle led him to remark upon the singular fact that the fauna, which immediately precedes that at present existing in any geographical province of distribution, presents the same peculiarities as its successor. Thus, in South America and in Australia, the later tertiary or quaternary fossils show that the fauna which immediately preceded that of the present day was, in the one case, as much characterized by edentates, and in the other by marsupials, as it is now, although the species of the older are largely different from those of the newer fauna. However clearly these indications might point in one direction, the question of the exact relation of the successive forms of animal and vegetable life could be satisfactorily settled only in one way, namely, by comparing, stage by stage, the series of forms presented by one and the same type throughout a long space of time. Within the last few years this has been done fully in the case of the horse, less completely in the case of the other principal types of the ungulata and of the carnivora. And all these investigations tend to one general result, namely, that in any given series, the successive members of that series present a gradually increasing specialization of structure. That is to say, if any such mammal at present existing has specially modified and reduced limbs or dentition, and complicated brain, its predecessors in time show less and less modification and reduction in limbs and teeth, and a less highly developed brain. The labours of Gaudry, Marsh, and Cope furnish abundant illustrations of this law from the marvellous fossil wealth of Pikermi and the vast uninterrupted series of tertiary rocks in the territories of North America. I will now sum up the results of this sketch of the rise and progress of palaeontology. The whole fabric of palaeontology is based upon two propositions. The first is that fossils are the remains of animals and plants. The second is that the stratified rocks in which they are found are sedimentary deposits, and each of these propositions is founded upon the same axiom, that like effects imply like causes. If there is any cause competent to produce a fossil stem, or shell, or bone, except a living being, then palaeontology has no foundation. If the stratification of the rocks is not the effect of such causes as at present produce stratification, we have no means of judging of the duration of past time, or of the order in which the forms of life have succeeded one another. But if these two propositions are granted, there is no escape, as it appears to me, from three very important conclusions. The first is that living matter has existed upon the earth for a vast length of time, certainly for millions of years. The second is that, during this lapse of time, the forms of living matter have undergone repeated changes, the effect of which has been that the animal and vegetable population, at any period of the earth's history, contains certain species which did not exist at some antecedent period, and others which ceased to exist at some subsequent period. The third is that, in the case of many groups of mammals and some of reptiles, in which one type can be followed through a considerable extent of geological time, the series of different forms by which the type is represented, at successive intervals of this time, is exactly such as it would be if they had been produced by the gradual modification of the earliest forms of the series. These are facts of the history of the earth guaranteed by as good evidence as any facts in civil history. Hitherto I have kept carefully clear of all the hypotheses to which men have at various times endeavoured to fit the facts of palaeontology, or by which they have endeavoured to connect as many of these facts as they happen to be acquainted with. I do not think it would be a profitable employment of our time to discuss conceptions which doubtless have had their justification and even their use, but which are now obviously incompatible with the well ascertained truths of palaeontology. At present these truths leave room for only two hypotheses. The first is that, in the course of the history of the earth, innumerable species of animals and plants have come into existence, independently of one another, innumerable times. This, of course, implies either that spontaneous generation on the most astounding scale, and of animals such as horses and elephants, has been going on as a natural process through all the time recorded by the fossiliferous rocks, or it necessitates the belief in innumerable acts of creation repeated innumerable times. The other hypothesis is that the successive species of animals and plants have arisen, the latter by the gradual modification of the earlier. This is the hypothesis of evolution, and the paleontological discoveries of the last decade are so completely in accordance with the requirements of this hypothesis that, if it had not existed, the paleontologists would have had to invent it. I have always had a certain horror of presuming to set a limit upon the possibilities of things. Therefore, I will not venture to say that it is impossible that the multitudinous species of animals and plants may have been produced, one separately from the other, by spontaneous generation, nor that it is impossible that they should have been independently originated by an endless succession of miraculous creative acts. But I must confess that both these hypotheses strike me as so astoundingly improbable, so devoid of a shred of either scientific or traditional support, that even if there were no other evidence than that of paleontology in its favour, I should feel compelled to adopt the hypothesis of evolution. Happily, the future of paleontology is independent of all hypothetical considerations. 50 years hence, whoever undertakes to record the progress of paleontology will note the present time as the epoch in which the law of succession of the forms of the higher animals was determined by the observation of paleontological facts. He will point out that, just as Steno and as Cuvier were enabled from their knowledge of the empirical laws of coexistence of the parts of animals to conclude from a part to the whole, so the knowledge of the law of succession of forms empowered their successors to conclude, from one or two terms of such a succession, to the whole series, and thus to divine the existence of forms of life of which, perhaps, no trace remains, at epochs of inconceivable remoteness in the past. End of The Rise and Progress of Paleontology by Thomas Henry Huxley.